record this one. Okay. And uh, so I'm gonna go ahead and get the assignments. Final exam. Let's see what the final exam. So we can proceed. It's very short and sweet because I'm not making the exam. All the exams, all the assignments, quizzes, and all kind of stuff been already set up when we were teaching online for our convenience, because we don't have to worry about anything. And plus that, okay, let's wait a little bit. Angela is done. Hi, Angela. Good evening. And then we just started. Okay, you didn't miss anything. Okay, so we were talking about that pretty much the homework 3, 4, and final exam at the same time. I'm talking about that one. So I was talking about that since that for homework 3, the last question should be based on these ones. Okay, the stepwise backward, like now question number 5. Question number 5, if you go ahead and look at that one, you can see that, okay, I'm talking to everybody. Okay, so be this pretty much based on this one. Selection procedures should be applied over there in order to come up with the best model at the end of the day. We were talking about several selection procedures.
I don't think you're sharing your screen.
Oh, you cannot, I'm not sharing. Oh, I'm
No.
sorry. Nobody told me. Nobody told me. Okay, that's right. I'm so sorry about that one. Okay, now you can see. Yeah, good. Okay, so here that homework. Yeah, here. There you go. See. So on the other hand, that we were talking about that the forward selection, backward selection. This is the homework 4 actually. I'm working on homework 4 right now. Not working that. Just to have a look at it. So these methods been already been utilized even in homework 3, because the number 5, question number 5 should be that answered with the aid of all these. I think you can remember that if you go ahead and pull out that one. Okay, rid of that one. Looks like that this wasn't okay. No, sorry. Okay, good. Okay, homework 3. So what I'm gonna say, even though I put over here, this is what I want to make it very clear one more time. Okay, so this one, this one, see, I put this one actually. I just put this one beginning of extras. If you really want to model that particular data, you can just do the same thing with the aid of the men or women or just the levels of the languages. That's the one that I'm doing over here. So like instead of putting that gender, you can put the either women or men, or instead of putting the language reg, the one that I was using earlier, being split into 2 parts and then using like this way French and English. And then that's another way of fitting this data. I stop over here. But again, number 5 should answer with the aid of all these all the way up to here again. Okay, then that means we are trying to get the best model. Then now extra part done. Now we go to the all possible models. You can go either with the language, reg, and gender, or the with the women, French, English, like that. See, again, I was doing that one again, 2 sets, but the same thing being done again. All possible methods should be done. Okay, with the aid of that language reg and gender for that 2 categorical variables, gender and this one. This is how we're going to get the R squared, adjusted R, CP, RMS, and I'm interested in only one option per given each category. Okay, so in that way that is we can easily be narrowed down to that what we really want, that one. And I did that one for wages versus all these, plus log wages versus all these too. You don't have to do, but I did that one. And on the other hand, other selection procedures being utilized here, forward selection, backward elimination, and stepwise, with the aid of this one. And it has been done for the log as well as for the log wages. Sorry, wages plus log wages. See? Right there. So the log wages has been already been created in that particular data set. In that way, you don't have to worry about that. Okay, that's one way of doing that one up to here. And then you're going to select. You can go with the wages only. Okay, here, wages and fix this one. Let's say, for instance, If you do this one and this one, more than enough to answer that one. That means this one, from this one, you came up with some kind of the best model. That best model can be convinced by the other procedures like this one. These two together, and this one go together. You don't have to necessarily do that. Or again, what I'm trying to say, instead of that using the gender, you can use that women and French English, that setup. And see, for the same setup, I did this way and log wages. And again, for the selection procedures, again, wages and log wages. So in order to answer that question 5, you don't have to do all of these. But if you can try all of these, that's far better. You can simply say you decided to come up with all possible model with the aid of gender and language for the categorical variable, plus its selection procedures. That's enough. Or these two. That's enough. Or these two. This one and third one. That's enough. Or this one and this one. Okay. In another way, I can put all these together. I'm going to take this out from here. But then right in the close. That's it, go together. All possible models under that one copy of, but all possible models. So instead of Y, I'm using right, not copy paste. So log to log, all and selection procedures. This one all to log without log. But this time I'm using that French English and women here. Again, the same setup. But this time I say gender and this guy I'm going to take out. For the log. Get together, and this one again under this one I can say all possible. These two go together. If you come to that one, see, you have to make sure that you run this one for sure if you're planning to use that one. Okay. See, that means that if I get this one clearly, I can put all these forward selection, French one, this one, and without up to here, I'm gonna cut and put inside that extras. Okay. Forward selection. This. And planning to do the extra one. So you're gonna do this way, you're gonna transform like this way, and then instead of using gender and language reg, you can go with the women and French and English. Women or men, doesn't matter. Okay. That's all the collection based on those things. But again, you're gonna start from here to come up with the regular one, either this set or this set. Then when you come to the fish, if you want to do the same thing again, you can get the SAS help has the fish, it's easy. If you go to the SAS help, it has the fish data set. So from there you get that one and then work on it. And number 2, pretty much the same way. Instead of wages, they say us to take the weight as our y variable. For the x variable, you can take any of the quantitative variables. They haven't very particularly say anything about that. Now I pick the height. If you want, you can pick the height or width and length 1, length 2, length 3. Okay. That's different. Species, weight, length, length 2, length 3, height and width. So I was using just the simply the height type. So height here, see, by species. And then I put the regression line as well. For different species, there are 1, 2, 3, 4, 5, 6, 7. So that one is in this SAS library. Okay. So then we use the all that categorical variable, sorry, numerical variable to fit in this one for the multiple regression. And we tried this one even using the length square. Okay. That's something not related to this one. Something just we were trying that one the other day. So we can put in here if that okay, then we can get this one. Cut and paste here. Yeah, it's number 3. See, so all this here we will try with the length, weight and length, and if you want, you can say height. Since we have tried height and height squared, if you want, try that one too. If it's not gonna give like a very clear that linear path or linear graph, you can square and then put it that one to add in another higher order term. You can write like that. We make sure you use the procedure GLM procedure. The number 3 that this means that regress with all the numerical variables are available: length 1, length 2, length 3, height and width. And then they've been, you have to make sure that they want to be transformed into log, because the log has not been already calculated or computed for us. So I'm going to say I go to data. This is my where the data was earlier. Now I'm going to give the new place, the new place. First this set and then I call the new place. Okay. This is where you had the old data. This is the old data set. It's like you have old data. This anywhere you can put it back. I'm going to get it from the SAS setup and then put it into the work, because I don't want to mix up. I think on the other hand, we cannot do the changes if it is in SAS help. So that's why I decided to put into a new folder called the work. It's a temporary work, that folder. It's the new one, okay? Data, not that this is not where the data is. This is the where the data is going to go to. This is where the data was. SAS help had the data, same like here. Then I'm going to put it into work, and now I work with the work folder. See, it's in that directory. So see, and then we get the log. We transform that one into the log. We took the log of that one and call the log weight, and we're gonna call that one and then work on that one. And here, see, all this. Put this one. Log weight. Something is missing here. Look, like the weight was missing. Something. Missing. Yes. We can take out if you have missing data. Okay, we know how to take this out. So then you can do the regression. I'm going to go to the work count. Work directory has that fish data. Okay. That's the one I'm gonna recall over here. Regression, ANOVA table, all kind of information we have over here. See, look at the 93%. It's a very well that explained. I mean, like a lot of variations. See, almost like the unexplained the variation or unexplained error carried from the empty model being 100 out of 100, that 93%, 93 of them being explained. Like if you carry 100, 93 being explained. If you carry a certain number, so much as a percentage, 93% being explained. So see, then on the other hand, then later on we want to just to fit in this one into our our model the same way we did that one in the previous case, previous data set, the language as well as that gender. We have only one categorical variable. That category variable you cannot keep it that strings. Strings should be converted into the numbers. In numbers, you can give the numbers and then run. The same to that. So I get the work. See, my data was here. I put it back into work again. And work in that. All the point estimate, they are standard errors, t-value, p-value, ANOVA table, r squared. See, that once you introduce those two, see, those one species, it's going to go down. See, better off to take or keep it, doesn't matter because it's 90%. Then get the all possible values that you see. I didn't do that log one. I just simply did these two. See? Then you can run to get the all possible outcome. See, 1, 2, 3, 4, 5, 6. No, 6. 6. Then let's say that how this works. I want to get this best. Let's say that put this one and then run and see. It should show all the possible outcomes. It's gonna happen in the blue color because that it's like there's a function in that name. So you know how many, okay? You know how many. You know how many possible. Yeah, this one, this one, this one, this one, this one. You know how many. How many we're gonna get because it's based on that how many variables we have. So we have how many variables here? All possible one. 1, 2, 3, 4, 5, 6. That should be 6 squared, which is 36. 36. Then first one, how many from the ones, single ones, like let's say 1, not only length at a time, length 1 at a time, length 2 at a time, length 3, length height, width, space. So there should be 1, 2, 3, 4, 5, 6 for sure because they were singles. 1, 2, 3, 4, 5, 6. On the other hand, this should be what? 6 choose 1, which is 6. And the second one should have how many of these? 2. 6 choose 2. 6 choose 2 means a 6 combination 2, 2 at a time. 2 at a time. That means if I this one, 6 choose 2 would be how many? Go to this one. This one. Look at this frozen. Okay, while I'm getting rid of this one, and then reconnect again, I can open again. While it's opening, we can talk about this answer. So just should be 6 choose 2. 6 choose 2 is how many? How many of doubles we have? That means you get the 2 times 1 for the denominator. On the top, you have 6 times 5. So the 2 and 6 get cancelled off. 3 times 5, 15. Let's say 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. See? 50. Then the next one, 3 at a time. 6 choose 3. That means you have a 3 times 2 times 1 for the numerator. Denominator on the top, you have 6 times 5 times 4. So the denominator, you have a 3 times 2 times 1, 3, 2 times 6, 6, and that 6 get cancelled off. You are left over with 5 and 4, which is 20. You should have 20s of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. See, 20 of them. 20 of them. Okay, that means like a, so I show that one too. That means that this one, 6 choose 1, see, single, see, 1, you have a 6 choose 1, which is 6 for sure. Then 2 doubles, 6 choose 2 means 2 times 1 on the top, 6 choose 5 is 15. Then three of them at a time. How many those combinations? 6 choose 3, which is 3 times 2 times 1. On the top, you have 6 times 5 times 4. That's a shortcut. So this one here, 2 and 3. That's how we 15. That's how we get 20. 15. Then 4 of them. 6 choose 4 is same as 6 choose 6 minus 4. You go to the shortest one. 6 choose 2. You already know 6 choose 2. Again 15. And 5 of them. 6 choose 5 means you can go to 6 choose 6 minus 1, which is 6 choose 5. 6 minus 5, which is 6 choose 1, which is 6 again. 5 and 6 is nothing but 6 choose 6 is 1 more. And altogether 15, 30 plus 50. How many we have? 6 times 6, 36. No, let's say no more than that. Let me see how come. Let me see this one. Then 4, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's right. Then the 5s, 1, 2, 3, 4, 5, 6, 6, only 1. So when they add to that one, 30, 50, 56, 57. That not comply with the 36. Can you remember that they were should be, let me see. Go back to possible combinations. All the possible combination, did we miss 50? And there's a one more too, empty model. We are missing that one for empty model as well. Empty model. One should be for the empty model. That's 0. See? 0, empty. See, that's one is nothing but 0 means that empty model. Empty model is 1, 2. So here 20, 15. 20, 56, 57, 58. No, sorry, I'm missing something here. Sorry, 30, 20, 30, 50, 56, 62, 64. 64. Did we see 64? How many we have? 1, 2, 3, 4, 5, 6. Why 64? 20, 30, 56, 62, 63, 64. That means 8 square. Why 8 square? Let me see. It should be all the possible outcomes. We have this one. You can remember. Yes, 64 8 square, including what? No, including what? So, okay, there are k variables to consider. See, and k squared subset. For example, with only k equals 5, there are 25 regression equations. Obtaining these sound like a ton of work. Okay. Then we went to this example. This example has n equals 25, 1, 2, 3, 4. Okay, then we consider only 4. Then we had advertising bonus, market share, and competition. We didn't take into account region. See, region we're not going to count here. 1, 2, 3, 4, 4 times 4, 16. So here is the problem. What is the problem here? How many we have? By 64, it looks like 8 square. But these numbers go with the 6. What happened? 1, 2, 3, 4, 5, 6. But altogether we have 64. I think this not doesn't comply with that one. Where this 8 square come from? Fish talking about this one. Oh, let me see. Because I'm looking for all possible ones. This one, see, each group we already found that each group. Let me see. I'm gonna put it back and see. Did I do any mistake in it? Here we say 15. No, we counted. We had a 15. 2 for the 2. For this one, we had a 20. Again, for the 4, if 4 one has a 15. 1, 2, we counted early. And then 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15. See? For the 5, 1, 2, 3, 4, 5, 6. And single one, this is 6, this is 1, this is 15, this is also 15. And this is 20. Yes, the mistake. When you add all these, they would not add to 6 square, they add to 8 square. So this one, whatever they say here, because I normally don't go by this one, I just calculate all the time. I do with the combinations. But this one sounds, looks like, see, if there are k variables to consider, k x variable to consider, then this should be k squared possible subset. No, it's here you see that we did this one too. We did the, sorry, for this one. It's consistent with that one. When we calculated with the aid of, not like that, by taking the combinations, when we were using the combination, it was consistent that time. And remember that we were doing, I can't remember that we were calculating. See that one, not here, no, see, something here. Okay, see here, 4 choose 1, 4, this is 1, 4 choose 1, 4, and double, see, 6, and 4, 3 variables, 4 variables, 4 variables, 1, 3 variables, 4, here 2 variables, 6, and 2 variables, 4, this one, the 1 plus 4, 5, 6, 11, 11, 15, and 16. That's 16 and 8. So in a similar fashion, if that's the case, we should go with this one. See, this combination. See, this way. I don't think it's like a 6 square. See, here I see that 64. Okay, anyhow, okay, the main thing that we go by these all the combination, but even though all the combinations, pretty much that instead of this one, we're gonna put, if you put the best one out of all these, even in the every category, you can go to the best one, and we can get the best one. You can easily narrow down. See, then you know, I'm not gonna display all of these from each category. It's gonna show that best one. See, very easy. Then now we can narrow down and then go and pick the one with the that you know the criteria. R square should be the highest, R star square should be the highest, CP should be smaller because the smaller the better, because that it's going to become unbiased. Otherwise, it will become biased for the large ones. Root mean squared means the error should be minimized. So if you go ahead and look at the one with the 89, 99, okay, this one 89, 67, okay, this one was 89, see, that's okay. And this one, see, 89, 93, 89, 67, the lowest one, and the lowest two, see, 40. So looks like this one. Length 3, height, width, step. No, highest 89, 93. This one okay, but out of all this 89, 67, they both okay. But when it comes over here, pretty much the both will go over there. But this out of, you can pick this one best. Okay. And the next one would be something like this. That discussion should be built up, and then we got here length 3, height, width, spec, then 3, height, width, spec. Let's see that if that's the case for by running for the same, oh, sorry, this one data script should be work dot fish weight, length 1, length 2, length 3, height, width, spec. See, significance levels to stay before he will taken out, or that significance level to enter, even for enter. We had that broader discussion the other time. See? So we use the GLM select and see whether it's going to pop up. Okay. See, it will narrow down to this time length and the width only after with that method. See, it has dropped one of the variable we had in the other method. So you can think, just try this one with the forward one and see what's going to happen. So let's see, the forward one is the same case. And 3 and width, and 3 and width again. And let's do with the stepwise. Okay, let's do the back one. Middle one. This one. But will produce the same answer. See, this time length 3, height, width, and spec. See, something we got with the pretty much length 3, height, width, and spec, very consistent with what we got with this one. Can you remember? See, length 3, height, width, and spec. See, 4 variables. Actually, 4 variables are the same. So you can build up the discussion. You say with this method and this that method being convinced by the another method, because of that reason, I'm going to go ahead and pick this one. See? But you cannot arbitrarily throw more variables. That's the same thing. That's the kind of like a discussion we're going to build up pretty soon under the principal component in order to answer that homework 4. So see here 4 variables, but that with the 4 variables, you can check and see that how they are, that the regression, sorry, R squared, see, R squared a little bit higher, see. But pretty much all these, even with the length 3, but we have a serious issue with the CP. That's why these two are not utilized in order to just to make the decision at the end of the day. They will be scrutinized by through this CP as well as root mean square. See, massive error that compared to 115. Why are we not going to go to the best? Always in statistics, we don't have something called the best, but we sometimes call the best. It's called the BLUE, best linear unbiased estimators. Blue, BLUE. That's like an acronym to when you're gonna expand it. B stand for the best, L for the linear, and U stand for unbiased, and E stand for estimator. So same way, like we go to the best as much as we can, but okay, whether we have all the procedures to that verify. See, when that method, you feel like you very kind of like you were contemplating whether I'm going to go ahead and pick that whatever the results we have over here based on our criterion, or is there any way this can be even being tested? Same way like a golden rule. Can you remember we were talking about a certain point? You go to get something for the like some kind of a test. You do that. It's called the golden test. Will be tested against with another test. It's you say in the beginning you say that H naught is true, H naught is false. Again, H naught is true, H naught is false. Can you remember we were talking about the contingent table at a certain point? But I don't want to get back to that one. But anyhow, so in a similar fashion, that this will be again checked by the other procedures. Okay. So that's how we're going to answer that one too. Like that. But anyhow, that since that in the very beginning I was talking about our homework 4 is not is based on either principal component analysis or factor analysis, or again this one same thing that we were talking earlier, that multiple regression and all that variable selection procedures. Okay, because of that, not with the ANOVA, we were supposed to go to analysis of variance, next topic. This one I'm talking about, this one, chapter 9. Okay, I think we better off to form because we don't have that much time. This one we saw at a certain point. This one we saw means like we saw these assumptions we saw. Only difference where the ANOVA is utilized. Same formulas we have seen in the this one. Sorry, this is a bit rigorous because getting rigorous, but you don't need all of these. So in this one, it's a very broad section in statistics, but very similar to that regression. Very similar to regression. Regression, we saw this kind of formula. So only difference for the X variable, you're going to have a categorical variable. The same way we were talking about over here in this homework 3, can you remember? At a here or here, let's say that here, species. With the fish data, see, only with the species. If you run weight with respect to species only, that's called the analysis of variance. Without these two. In another way, that's called, can you remember we built up our discussion in the beginning, empty model, group model, regression model. Group model has another name. I told at that stage when I was talking about analysis of variance. That's the same thing. It's like a categorical variable for X variable. When you have a categorical variable for X, for the horizontal axis, then you can have some kind of procedure called the analysis of variance. If you have just this one only, numerical variables for X variable or regressive variable, then you can have a regression. Or if you have a combination, combo, still you have a regression. Still have a regression. But if you have only this one only, we'll regress this one, then you're going to say either group model, group regression model, or analysis of variance. In that way, we don't have to particularly go through this one again. And that's why it's pretty much the same concept that we saw in regression. But it's a very, very very broad section. See, broad section. See, there are so many things we have to discuss on this one, but it seems like it's the same thing that we saw in regression in that way. See, they go to that all the these are we don't have to use the formula when you run this all the procedures on SAS. They're going to produce that one. Even with that one, since we don't have any test on that one, I'm going to skip this one and then move on to principal component analysis. Okay, so let's talk about this one. In that way, you can easily answer this one. And under the later on that the principal component analysis, and I would like to, if time permits, go to during these 3 days. If I like to go through the discriminant analysis and logistic regression too, because the discriminant analysis, logistic regression, those kind of stuff gonna be the part of the principal component analysis. Those are part of the machine learning. Okay, you know that one. Those are part of machine learning. In the machine learning that we mainly have, let me see, we mainly have data mining. See that mainly that if you go ahead and look at that the data mining, as you know that there are two types in data mining or machine learning. There's one called the supervised learning. Under the supervised learning, we have linear regression, logistic regression. Linear regression we did. Supervised learning. Under supervised learning, we did the regression. Then logistic is this part. Logistic means for a y variable, you have a two options only. Yes or no. Whether before you're gonna get somebody being hired to a company, you're gonna see whether this person gonna produce or gonna be like a very high performing employee or not. High performing employee or not, based on the previous data, you're going to build up some kind of a model to predict that the newcomers, before you're going to hire, you're going to fit in into that model and see whether they're going to fit in. That particular person should be hired or not. That's why we are building up that regression model. When we're going to manufacture some kind of that electronics, electrical, mechanical, or chemical that components, we use that one too. Yes, no, defective, non-defective. So that when Y has a two-way options rather than one options, rather than having the quantitative variable the way that we used to have a height and weight, then you use that one. And there is another part is a discriminant analysis too. If I get back to that supervised learning, under supervised learning, you have a linear regression, logistic regression, time series, classification or regression trees, neural networks, and k-nearest neighbor. Those are the ones going to come under that supervised learning. Under the unsupervised learning, you have a clustering, association analysis, and principal component analysis. So in order to become a data analyst, okay, data analyst, we really need to have a very heavy background on that statistics part. It's a key part. It's not about you're going to jump into that machine using machine learning, no, the deep learning, no, artificial intelligence, or neural networks. Neural networks being explained by the Bayesian analysis in large scale at the end of the day. But when you go through this, all the classes, when you build up this knowledge piece by piece, I think you're going to be an expert on that one too. Okay, right. Okay, let's go ahead and look at the principal component analysis to get like a rough idea what's going on. But in order to get this a clear picture, I would like you to have a look at this one. Okay, it's already been done. I hope not this one. Is that the one? Not this one. Let's see the context. Okay. No. Is that the one? Let's see which book has that. Is that the one? No. Where is that one? I had that one already. Oh, here, there you go. Principal component analysis, we are not doing theory, any heavy theory we are not doing over here. We are not going to do any proof here. I'm trying to show you the process for you to get a clear idea. But when you go to this one, okay, when you go to this one, see, it's like a one line. Okay, in order to get this done, one line. If you want a principal component analysis, see, you use the factor, ST okay, those things to that. See, print com, that's it. That will give you the principal component analysis at the end of the day. But the thing is how to interpret at the end of the day. When you see the result, how could you gonna interpret if you don't know the background behind that one? Okay, this is the homework 4 based on this is part 2. That's for the multiple. This one for that one we were talking about get any data of your own and then just working on that one. See, and you can get the data like this way and working on that one. So many things we can talk about here. See, you use the factor or you can use the factor analysis to PCA. See, and so many things we can talk about during this discussion today and then mainly that Wednesday and Thursday or during this week. Okay. So, but in order to interpret that whatever we're gonna see when we run something, okay, let's say that let's get this data, okay, a PCA, GSP, CSP data. So I hope you guys have those data over there. If not, GSP, that means that this is for the principal component analysis has been done for that gross state product, like a national income in a particular state. Let's see that. Well, let's go to data. GSP. Do you have that one? Oh yeah, see. Okay. See, these are the data being given for that, how they're gonna get the income through which industry for each and every state. See, for all these 50 states. Okay. So they have agriculture, mining, construction, manufacturing, transport, commerce, energy, trade, trade again, then our services, government, and all kind of that sectors that will produce that the national income for each and gross state product. GSP stands for the gross state product. That's data set already over there. You can utilize that one. So you don't have an issue on that one. That's the data set we were using. See that let's say that I'm gonna show you this one and see why I really want to explain that one behind those things. Okay, so that is it's already over here. Data services government, and let's say that we are trying to get the correlation. Okay, I got this data. They were in, I think, work directory because the things we have not. We're gonna call the name GSP. Okay, and I go and then call the GSP, and then I need the covariance as well. Covariance. Co stand for covariance. It's a the correlation matrix. So this one correlation. I'm sorry. This one correlation. This one covariance matrix. See, it's a covariance. How the correlation and covariance, how they are related. See this one. See again against each other. See AG versus mining, AG versus construction, manufacturing, energy, transport, see construction, energy, trade, RE services. See? And pretty much the same thing here. So how they are related? Covariance. How do covariance and correlation are related? You know, covariance is nothing but, correlation is nothing but the ratio between, I'm gonna go back to this one and get this one open up. Okay, go here. This one. So correlation between, see, I'm gonna say correlations between two variables, any two variables. So x and y is nothing but covariance of x comma y divided by, see, standard deviation of x times standard deviation of y. That's how they are related. So the covariance is, if you want a covariance, that means you have to multiply correlation between those two variable times the standard deviation of one variable and standard deviation of the other variable as well. See, this is how they are related. So that's pretty much the same thing. But in our discussion, in this principal component, we pay the very heavy attention for covariance. This is the guy playing a heavy role. Okay, this is the one we're gonna split. That means in principal component analysis, what are we gonna do? We were just looking at our model. Let's say that you have thrown like a 5 variables, 10 variables. Then look at the variables 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So many variables, 13 variables being thrown to the here in order to explain that gross state product or the gross national product or the national product of a state, the national income of the state. So those 13, wow, so heavy. And I mean like those, it's some, there are some variables not even very importantly contribute in explaining the variation of that national, GSP. Because of that reason, we are trying to not to get rid of. Last time in the selection procedures, we got rid of them. We're not gonna get rid of them. What we're gonna do with the aid of that one, we are trying to reduce the dimension. Here we are working on 13 dimension. See, the 13 dimension. This is 13 dimensions. We cannot work with the 13 dimension. We love to work with like a 2-3 dimensions. But how could we can reduce that one to the dimensional reduction procedure is called the principal component. How could we gonna change that one without taking out any of the variables? Then they came up with a new procedure. What they're gonna do, we're gonna write their new variable called the principal component, PC1, PC2, like that, in the aid of these variables as a linear combination of these variables. Now it means a linear combination. That means that this one plus this one plus this one plus this one, blah, 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 like that. But you cannot arbitrarily add those 13 variables together and say, come up with a new variable called, let's say, principal component 1. That's not enough. So then when you're going to add these together and say, hey, it seems like a one, you can reduce that to 1 dimension. No, it doesn't work like that. Every time you're going to add those, every variable should be weighted, like in weighted average. How much weight should be put over here? You put a certain weight based on what? Their own information. Look at their own information. See, certain weight. See, if you go to that your original data set, this is the weight. Some weight has to be included. How much the weight would be? How could we know how much we added to that one? That's the discussion we can try to build up. Those weights are called the eigen vectors or eigenvalues. Those are the ones that we're going to little bit talk about that one. We don't going to go to the mathematical aspect that one, but I'm trying to give you like a clear, like a rough idea how to get this done. Later on, based on a certain criteria, we're going to say, I'm going to write the linear combinations, several linear combinations. How many linear combinations of this one I can write? 13 of them. Again, I have an issue. If you are not working with 13 and if you come up with another linear 13 combination of this one, then we have a criteria to weed out unnecessary linear combinations. That based on the Kaiser rule, we're going to take them out. When we take them out and then keep the number of linear combinations we're supposed to keep over there. Then let's say that we have 13 dimensions, and based on that Kaiser rule, that you're going to leave only 3 principal components, 3 only combinations. Those combinations are referred to as the principal component, PC1, PC2, PC3. Then you are working with 3 dimension rather than working with the 13 dimension. That's a dimensional reduction procedure. Okay. So how that should be done is the discussion we're gonna build up over here. Okay. See, let's say then now I'm gonna run this one. See, GSP data. Let's say that let's run the principal component. Okay. AG mining construction 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's see, let's say that this N5 I'm gonna keep for time being. Okay. Let's see what's gonna happen. Print com. Okay, let's see what you have over here. See, you have each variables mean and standard deviation. Mean and standard deviation. How many observations? 50. How many variables? 30. Each variables, for if you're gonna add all that GSP for each and every state and put together and then divided by that 50, you get the average, the standard deviation, see, for each and every variable. And correlation, this is the key part. You're gonna come up with something called the eigenvalues of the correlation matrix or covariance matrix. Okay. Eigenvalues. See, some people pronounce this an eigen. It's a German word. Eigen. See, eigen. Most of the people they pronounce eigenvalues and eigenvectors. See, they are corresponding vectors. These are the weights. These are the weights. See, the weight has been put and then they built up principal component 1, principal component 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. These are the weight. This weight will be put it into this guy. This is the weight. This much of weight times AG plus this much of weight plus mining. That's for the first principal component. This much of weight plus construction. This much of weight plus times manufacturing plus this times of this one plus this time that plus this time that plus this time. These are the weights for each and every variable. This is the second principal component. This is the third one, fourth one, fifth one. But as I said in the beginning, I'm not planning to go with all these 13 components. What's the point? If I opt to not to work with the 13 variables and then I'll again come back and say, I need the principal component, 13 component. No, I don't need that. That part will be determined by eigenvalue versus principal component, this graph. That graph, anything, see, 1, see, that's what the Kaiser say. See, anything below that one should be taken out. Anything above that one should be the one that we're going to take into account. Because look at the principal component 1, principal component 2, principal component 3, 4, 5. Up to 5 is enough. These are negligible because their contribution is negligible. Their contribution is negligible. The variance, eigenvalues means nothing but the variance of each and every variable. You can see that. These are the eigenvalues. These are their corresponding eigenvectors. I'll explain you what those are. Okay, that's why I say I need to explain you a little bit about the eigenvalues and this is it. This is the eigenvalue. If you have a 13 variables, 13 eigenvalues. If you have a 13 variable, you have a 13 eigenvectors as well. This is the eigenvalue. This is the difference between what and what. This is between these two adjacent eigenvalues. Two adjacent eigenvalues difference. Two adjacent eigenvalues different. And keep going. Two adjacent eigenvalues difference. Proportion. That means this one divided by the total. This one divided by the total. This one divided by the total called the proportion. And this is called that's the cumulative of the proportion. You're gonna get this one. This will be added to the second one to get this one, accumulation. Or simply you're gonna add all the way up to this one. See, that's accumulation or cumulative. Cumulative means you're gonna add at the fourth level, at the fourth eigenvalue, how much accumulated? 67%. See, keep adding all the 5 together. 76%, 83, 88, 95, 97, 98, 99. So they are planning to keep only as we saw that 1, 2, 3, 4, 5 principal component. That's why we put over here n equals 5 based on the Kaiser rule. Kaiser says that any lambda means eigenvalue greater than 1 are the one that we have to take into account. That means this being again verified through here too. See, eigenvalue is 1 here. See, more than ones. How many of them? See, 1, 2, 3, 4, 5. See, those 5. So eigenvalues and those 5 will be keeping over here, and I'm gonna take the principal component related to those 5 for the print 1, print 2, print 3, print 4, print 5, print 6, and then work with this 5-dimensional, the 5 variables called principal component, which are linear combination of the given variables, linear combination of the given variables. See, that's the idea. So how do you decide from this one? It's not a big deal. So that's the whole thing over here. So you're gonna run that one, see? Then with the one line you can, but if you want, you can get some the data lines. You can just, rather than that important, you can have the data here too and work with that one too. See? If you want, you can go by n equals 5. Okay, now we know n equals 5 would be the one. Now, if you put n 5 and run this one and see what's going to happen. See, you're going to lift over with only the 5 principal components, the same thing that we were talking about, which are correspond to see, 1, everything more than 1. See, more than 1. Eigenvalue more than 1 are the one going to appear here. The accumulation, see, principal component and the proportion and the accumulation, see, all the way up to. So those 5 will be left over. You saw you working with the print 1, print 3, print 2, print 3, print 4, print 5. These are my y. Now this is my x, x1, x2, x3, x4, x5, and you're gonna get the y variable, whatever the y variable, that y variable will be regress with the print 1, print 3, print 2, print 3, print 4, print 5. That particular regression is called the principal component regression. You first built up the principal components. Principal means like a major component which has like a high variation or contribute in large scale, at least 70%. See, up to this point, see, look at this, the variation. Almost like a 75, 76, almost like a, if you're going to round up to this one, 80% of variation being explained. That's enough. Okay? That's it. It's been consistent with the Kaiser rule. Kaiser said that one, anything beyond any combination with the lambda more than 1, sorry, not the lambda called that eigenvalue more than 1 would be taken into account and kept in the model. Because these are taken into account, and then you can get the y variable and regress the y variable with the aid of these variables. These are now like a variable 1, variable 2, 3, 4, 5. We narrow this down. Okay. Like that. We can do this one even for this one. See, like the see method PCR method. In fact, how many factors? See, you can use this one too. See, like so many methods we have, but we can keep talking about those things pretty much. Or you can go to the factor to factor this the procedure and then get this done as well. And from the factor to how to come to the principal component, we can discuss everything while we are going through this one and homework and everything. Okay, but as I said, that I really want you to have a little bit clear idea about what the eigenvalues and eigenvectors are together up with it. Okay, let's see. Okay, I'm going to build up discussion this way for your convenience. It's not having math or anything like that, but you should bear with me because there are some matrices. I think you guys are working with, have worked with the matrices up to a certain point. Look at what will be this is what's going to happen. Let's say that you have 2 variables, okay, not the 13 variables. Okay, this is not a y. Okay, this I'm going to call the y for my convenience. Let's say simply you have 2 variables. Okay, in our discussion, we have 13 variables here. Can you remember 13 variables? See? Like you said, you have only two variables, agriculture and mining only. Okay, I'm trying to say that even for the two variables, eventually you can work with one variable at the end of the day rather than working two. Here 13 been reduced to 5. Okay, I don't want to throw that 13 variables or general now notations. So I would say that I have two variables, which is called x and y for my convenience. It's not the y variable on y-axis. Forget about that one. Simply you say there are two variables. And for your convenience, I'm going to take only three data points. Three data points for these or both variables. See, 1, 0, -1, -1, 0. Let's say this one agriculture data, this is mining data. See, only three data points or information or observed value. This one is like a kind of like a column vector. We call this one a vector. This is also a vector. So the vector will be having like a rows 1, 2, 3. 3 rows and 1 column. That's why we call this one 3 by 1 column vector. If it is row, this one is row. See, look at 1 row. That means you have a 1 row and 2 columns, 1, 2. That's called the 1 times 2. You write the row first, 2. So the similar fashion here. So each one is an observation, an observation, an observation. Put together, we call the data. Now what I'm going to do, I'm going to combine this data with this one. When you combine x and y, their data entries or the value is going to appear like this, like this. Now I have like that. So the 1, 0, -1 for x, 1, 0, -1 for this one, -1. This is something I made up, some numbers, okay? Okay, some number. There's no particular reason why I pick like this way, but I put this way that for my convenience, okay? Those are the values over here. Let's say that agriculture and mine, these values, okay? Instead of picking like all these, sorry, not in this way, sorry, should be in that original data set, okay? Original data set, if I go back to 6, there's that data set. Do I see something? Okay, that's okay, we can get it. Simon, homework for PCA, GST. Okay. I'm talking about that agriculture, this data, okay? Instead of going through these 50 data points, I just pick 3 of them. And then I don't call that one 2 or 1.5 or 1.7. I simply call that one 1, sorry, 1, 0, -1. The other one for mining, -1, 0. See, for my 1.5 to 2.4 and 1.3. Rather than that one, I'm going to call 3 for my convenience and then for the easiness of the calculations. Okay, so put like this and it appear like this. Now this is a matrix. This matrix has 3 rows, 1, 2, 3, 3, 2 columns. It's a matrix. This matrix. That's the data matrix. This is actually data matrix. This is a matrix. Data frame is a matrix. See? It's a matrix. See how many rows? 50 rows and how many columns? 13 columns, and including this one, 14. Okay? So 13 columns. We don't take into account this one variables on this. So what I'm going to do, I'm going to find the mean vector. Mean. You can remember that you have this one, you're going to add all these and divide by 3. This one add and divide by 3. The mean vector is 0. Mean vector is 0 and 0. X has a 0, Y also has a 0. Then we're going to build up something called the covariance matrix. Is nothing but S minus S bar. I'm going to call this one S bar. Transpose, because this is a matrix. Transpose, for the transpose, you can flip it. That means row becomes columns, column becomes rows. That's the idea. And then you write that this one as it is, S minus S bar. And when you try to get the covariance matrix, that row inside, I'm not talking about this side, within that one, you have these features. In here, you have the covariance between X and X, which is called variance. Here, you have a covariance between X and Y. And same thing will be repeated here, because through the diagonal, It will be mirror image. And here you have the covariance between y and y, which is called variance. On the other hand, as I said earlier, correlation is the covariance divided by the standard square root of variance, means the standard deviation of x and the standard deviation of y. And this one, if you run this one, then your covariance gonna be in that format. That means, see, I'm gonna, since I have this one 0, 0, I don't have to subtract. I'm gonna say S transpose. S transpose means you have this column, 2 columns become 2 rows, and 3 rows become 3 columns. See, flipped transpose. I rotate. See? And I keep the S as it is. And you're gonna multiply. Multiplication we don't do, okay? How multiplication means? First row, first column. First row, first column here. How they do? 1 to 1, 0 to 0, -1 to -1. Second row, first column. So second row, first column of C. How did you get that one? Second row, first column by multiplying these two one at a time, -1 to 1, 1 to 0, 0 to 1. And keep in head, this multiplication is possible. Your number of columns is same as the number of rows of the other one. If these two numbers are not the same, you're not gonna get this done. Actually, these two numbers get cancelled off. You are left over with 2 by 2. That's why you have 2 by 2. And you go to the third place. Third place called the first row, second column. See? First row, second column. 1 to -1, 0 to 1, -1 to 0. And the fourth location in C, which is the covariance matrix, -1 is second row, second column. -1 to -1, 1 to 1, 0 to 0. When you simplify this one, you get 2, -1, -1, 2. Those are nothing but, this is the variance of x, it's the variance of y, it's the covariance of x and y. That's been same thing being repeated under this one, since we have 2 variables. We have 2 variables. Very interesting. This is the covariance between those things. Covariance or correlation doesn't matter. Okay, because it's not a big deal. This can be multiplied by a certain constant to convert this into correlation. No, okay. Let's say the covariance based on that. See? The computer gonna do this one for us. That's what they were doing. When you have a 13, they have a 13 rows and 13 columns. See, the diagonal will carry the variance. The diagonal, see, will carry the variances. These are the key part. Now what we're gonna do? We're gonna split the covariance or correlation matrix into 2 parts. One called the scale part, called the eigenvalue. The other one called the direction part, called the eigenvector. How do you split this one into 2 parts? This guy will be split. This is the one who carry all the information. See, covariance matrix times eigenvector equals to eigenvalue times eigenvector. That's the setup. You have a covariance matrix. You have eigenvector equals eigenvalue times eigenvector. How many eigenvectors we're going to have? 2, because you have a 2 variable. How many eigenvalues you're going to have? 2, because you have a 2 variables in the beginning, x and y. You see? This is called C. I'm going to say eigenvector. U. Okay. U means eigenvector. Lambda means eigenvalue. This means eigenvector. In order for this matrix that I'm going to bring to this side, I'm going to pull out U, C minus lambda. Since I'm dealing with matrices, I'm going to put the identity matrix. Identity matrix here. See? Identity matrix. Yeah, identity matrix is like a C. Only diagonal will carry 1. It's a 2 by 2 as well. For this equation to be solved, for that to, see, this equation has to be solved in order to get the C. For this equation to be solved, the following has to happen. You have to solve this one. That means you get the C minus lambda U, this part, and take the absolute value of this one called the size determinant of that equals 0. How do you do that one? You put the C here, minus lambda here, and you're going to multiply by lambda, 2 minus 2 minus first if you simplify this one inside, first row, first column will be this guy minus lambda. See? The other one should be -1 minus lambda times c. First row, second column. Second row, first column means -1 minus lambda 0. And this location minus that location. Then you get 2 minus lambda. You get -1 minus lambda -1, 2 minus lambda -1. Then how do you this means a determinant. This is called the size of the matrix. How do you simplify? You're going to multiply these two with positively minus this guy. This multiplication. This multiplication means 2 minus lambda times 2 minus lambda, which is 2 minus lambda square. And minus time -1 times -1. Look like this. See? 2 minus lambda, 2 minus lambda, minus -1. So when you FOIL this one, 2 minus 2 to 2, see, first ones, outer ones, inside ones, last ones. That's a FOIL, you know that. So you're going to end up with the 4, 2 times 2, 4, 2 minus lambda, minus 2 lambda, minus lambda to this one, minus 2 lambda. Lambda to lambda means lambda squared. Here minus time -1, this one. Simplify, you're going to come up with the lambda squared minus 4 lambda plus 3 equals 0. This is called the characteristics equation or the eigenvalue equation. See? This is nothing but, you don't have to go in that route. You go to the covariance matrix. Look at, you go to the eigenvector, this one. It's nothing but the summation of these two called the trace. Sum of these called the trace of C. 2 plus 2, 4 gonna come here. See, that's how you got the 4. And the determinant of that one is how much? Determinant of covariance. I'm not talking about this guy. Okay, I'm not talking about this guy. No, I'm talking about C only. You can get the eigenvectors and eigenvalue only with this one rather than going through this rigorous process to get the eigenvalue. That's what I'm trying to show you shortcut. It's nothing but, this 3 is nothing but determination of this one. How do you determine? That means determinant is nothing but the size. How do you get the size? 2 times 2 this way, minus time -1. Same thing we did earlier. Okay, 3. Look at the 3. So it's a general setup. If you being given the covariance matrix, what they're gonna do? They're gonna add all the in 13.1. They were adding all these. Go to the correlation and add in all covariance. Okay, because the correlation you have 1. This is for the covariance matrix. Covariance matrix. You didn't have that. Can you remember? Let's say that it's a covariance. You're gonna add everything on the diagonal. That number is the one that's gonna appear for the second as a second term of this quadratic equation with the minus. And the 3 is nothing but the size of the covariance matrix. How do you figure out? When you have more than 2, they have a procedure. We don't gonna discuss that one. They have a procedure to calculate. Okay? So then they calculate and say the size of this guy. We can shortcut that one, how to get this quadratic equation of the characteristic eigenvalue equation. Then you solve that one. You solve it. How do you solve? You're gonna factor. You know how to factor lambda and 3 minus 3 and 6 minus 1. Lambda minus 3 equals 0. Lambda minus 1, 0. Then lambda has 2 values. See, I told you. If you have 2 equations, 2 variables, 2 eigenvalues. This is eigenvalue. Now with the aid of this one, let's see, I'm going to put a note here. Sum of the eigenvalue is nothing but the equal of the trace, which is equal to the trace of C. See? Sum of them is equal to the trace. Okay? See? So covariance means these are the variances of all the variables. So if you add the eigenvalues, that means eigenvalues are nothing but the split of the variances. They were certain way split. See? But their summation is same as the summation of the variances for all the variables. That's what we are trying to say. In 13.1, 13 variables, sum of the variances of the 13 variables would be same as the sum of the eigenvalues. So eigenvalues are nothing but the variances. The product of the eigenvalues, which is 3 by 1, 3 times 1 is 3, is equal to the determinant of that guy as well. So you can think about those two. In order to build up that quadratic equation, in order to build up this quadratic equation, you can use the shortcut as well too, like this. And after you solve that one, you go back when introspection, kind of like say, hey, 3 plus 1 is what? It's same as what you had in the middle. See? 3 times 1 is what? Same thing that you were having in the quadratic equation. Sorry, for the single term. That's the beauty of this one. So they all represent what? Eigenvalues represent the variances. Variances. Okay? So variances. So once you know this one, you're gonna pick one at a time. You're gonna say, for this given this guy, I'm building up something called the eigenvector. This is a procedure, okay? This is just write it, I put it back into the equation and solve. Okay, I'm not gonna go that and repeat it. Eventually, you get the eigenvector in this format. See? U1 and U1 like that, then 1 and 1. I divided that one by 2, normalized. I square this one, I square this one, take the square root and normalize and then divide it. See? This is your eigenvector related to lambda 1. Lambda 1. That's the one that you're going to appear here. This is what I'm talking about. See? See? Eigenvectors. For this one, these are the values that I'm showing over here. When you have a 13 variables, you have a 13 of them like this. When you have a in this line, when you have a 2 variables, you have a 2. See? 2. See? These 2. Related to whom? First eigenvector. So in that way, now you have a clear idea. These eigenvalues, eigenvectors are related to the eigenvalue here. This guy. The eigenvector related to 3.23551072 is. These are the eigenvectors. Eigenvectors, they were being listed in a vector. Like a first one, second one, third one, same way over here. See? See here. For the second eigenvector, I'm going to create another eigenvector. So that's 1 over root 2 minus 1 over root 2. So I have a 2 eigenvectors and 2 eigenvalues. Same way, I have a 13 eigenvectors. I have reduced this to 5. Okay, I have 5 of them because we reduced by using the Kaiser rule. K-E-I-S-C-R. Kaiser rule says that the principal component with the eigenvalues more than 1 should be taken into account. So the second one is related to this guy. Okay? This eigenvector. Okay? Third one is these are eigenvectors. Okay, it's not a principal component, even though they say they are related to principal component 1. I'm going to show you later on. You have to write. And this for the third one. These are the eigenvectors for the third eigenvalue. Fourth eigenvalue. This is a fifth eigenvalue. These are the eigenvectors or the components of the eigenvector of that particular, related to that particular eigenvalue. So see, 5 eigenvalues and they are corresponding eigenvectors. See? Same way that we are doing over here. I have a lambda eigenvalue 1 equals eigenvalue related to that one. This is my eigenvector. See, 1 over root 2, 1 over root 2. My second eigenvalue equals 3. My eigenvectors are eigenvector is 1 over root 2 minus 1 over root 2. Okay? This is the procedure of getting that one. The load-ins means, load-in vector means eigenvector. Each an eigenvector times the corresponding eigenvalue. So I'm going to go to the first one. That's the load being utilized in order to that get the weight. Load in vector L1 is, see, my first eigenvector multiplied by square root of its corresponding eigenvalue. Then multiply by this one each and every time. Your first load in is L1 is 1 over root 2 or 1 over root 2, same as the eigenvector. See, this one, same thing. And the second load in would be, according to that formula, they say that eigenvector times the square root of eigenvalue. So this is the eigenvector 1 over root 2 minus 1 over root 2. Second one should be multiplied by this one. Now what I'm going to do, I'm going to bring this one and then put it over here. See, 1 over root 2, 1 over root, sorry, not this one, 3 minus this. So these are the loadings for principal compound. This is related to X, this is related to Y. Look at the PC1 is nothing but 1 over root 2, 1 over root 2. I'm talking about this one. I'm going to write this way rather than writing this way. I'm going to write this way horizontally. Look at what I did. This way. Because this 1 over root corresponds to X. This 1 over root 2 corresponds to Y for the first one. With coming from this is the eigenvector coming from the first eigenvalue, which is lambda, for the lambda equals 1. This is the second eigenvector. I'm going to write this way rather than write this way. It's related to X and Y. So this is nothing but, see, X variables weight. See, that's the day mine in agriculture. See, agriculture being weighted by 1 over root 2. Mining will be weighted by 1 over root 2. And then I'm going to write as a combination. See, for lambda equals 1, principal component 1 means 1 over root 2 times X plus 1 over root 2. 1. See, now this is your principal component 1. So let's say this is agriculture, this is mining. They've been weighted by what? This guy. They've been weighted by this one. This eigenvector times this one. Then you can write the same way like we were writing over here. For lambda equals 3, principal component 2 will be this times X plus means minus this one. See, look at this. See? Those are loadings. Then we didn't talk about the communality yet. We talk about some properties of the lambda. We can remember. Now I'm going to talk about something called the communality. Means the total variance that can be each variable's total variance that can be explained by the principal component. What that means, after they have transformed, we didn't throw away any variables. I'm taking into account X and Y. X and Y will be, see, linear combination. See, linear combination. This is called the linear combination. If you write X plus Y or X minus Y with their corresponding weights, loadings, actually loadings, not the vectors actually. Don't use the word loadings. We have to go to that far too. Otherwise, that numbers not consistent. Go to loadings. Loadings will be how much load will be put on this X and Y to get the principal component 1 will be determined by the eigenvectors and eigenvalues. We know that procedure. Then we're going to say each variable total variance that can be explained by the PCs are called the communality. What that means, you see, total variance of the X, each and every variable. Okay, I'm going to take one better time. Total variance of X explained by the PC1. Now you get the PC1. From the PC1, how much of variation being explained by the PC1? Because earlier there's a certain variation for the X. Now principal component come and then dominate. But how much of X variables total variance can be explained by the new guy? This guy was earlier. Now this guy. If this guy take over, we want to know that how much of this guy's variation can be explained by this guy. That's what called the communality. So, and then in a pretty much similar fashion, I want to know that principal component 1 can explain how much of variation of Y. And then so do with the PC2 as well. So this is why we're gonna say total variance of X explained by PC1 and PC2 together. I'm gonna put together. See, see, each variable's total variance that can be explained by the PCs. See, PC1 and PC2 together. X variation can be explained by PC1 and PC together would be how much? I want to know how much of that variation being explained. That means this one square plus the other one square. I'm talking about this way. Okay. Principal component 1 and principal component 2 together, how much of variation of X being explained? Or variation of x being explained by these two together, how do you get this one squared plus this one squared, which is 2. We have plus 3 over 2 when you square 2. Similar fashion, coming with the 5 variables, variation, total variation, 5 variables, total variation. See, y variable total variation being explained by PC1 and PC together is how much? This one squared plus this one squared. Those are called communalities. So when you simplify this one, you get the 2. On the other hand, sum of squared loading is equal to the eigenvalue. Look at that. You go to the loading. Okay, I'm trying to, these are you already got. Now properties. Sum of squared loading is equal to the eigenvalue corresponding. See, go to the loading. Corresponding loading. You know how we got the loading 1 and loading 2. This one. If you go ahead and square this guy and add together, see, that will give you eigenvalue which is corresponding to this one. Same way, loading 2. If you square this guy and this guy, that would give you the eigenvalue of correspond to that one. On the other hand, sum of the communality is nothing but the sum of the eigenvalues or the variation, which is 4. Sorry, which is 4. See, communalities, if you add 2 and 2, that's 4. This is nothing but sum of the communalities is nothing but these are nothing but the variations. But how they split, they are nothing but the eigenvalues, sum of the eigenvalues. Sum of the eigenvalues, sum of the communalities, and sum of the covariance. See, sum of the covariance, sorry, here, see, look at the covariance vectors. So, here. Covariance vectors, these two. Trace, call the trace for this one. Or sum of the diagonal elements. Or sum of the variances. These are nothing but the variance. We told you, these are variance. It's a variance. Sum of the variance, the trace of covariance matrix. Okay. Sum of the diagonal elements, and the sum of the communalities, sum of the eigenvalues. That's the same thing. That's the same thing. That's the same thing. So that's the part that that means, see, that if you come over here, that when you split this one, you can remember the covariance being split. Now you can say that trace of covariance. See? I'm sorry, it's not right. Okay. Trace of x, y covariance. Trace. Can say the trace of covariance matrix. Same as, okay, same as sum of diagonal elements of covariance matrix, same as sum of variances of x and y, same as sum of eigenvalues. So one word, same as sum of community. The same thing. So that's going to be the same at the end of the day. So in this discussion, you know what this means now. Now, if you want to write the principal component 1, you're going to say print 1 equals agriculture, this value times. Okay? So that means that for related to this one. So at the end of the day, you saw that I go back to here. Yeah, here, 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 here. You saw at the end of the day how we wrote that PC1 with the loading. Now we have a PC1, PC2. Now let's use that. I want to go back to the Kaiser rule. Kaiser rule says what? Anything lambdas more than 3 would be taken into account. That means eventually you keep only this guy. See, lambda equals to 1. If you want, you can drop or keep it in this case. It's not a big deal, but if you strictly stick to that rule, you can say anything more than 1 would be kept in the model and the rest will be taken out. Then you can work with this guy. See, rather than working 2 dimension, now you can work with 1 dimension. 1 dimension. It's a 1 dimension. You have a new variable called PC, principal compound. Principal compound. See, you can work with that. See. So then if you have another y variable, y means like another variable, vertical variable, that variable can be regressed by this one. Regressed by this one. Regressed by this one. See? So in this case, you can say print. See, if you want to write for this one, you can write, these are loadings. Loadings. So you can simply say that principal component 1, I would say PC1 equals nothing but, okay, I'm going to write on the first one, 0.134820 times agriculture plus 0.469700 times mining, and then write the plus plus or negative 3.3, sorry, 0.3789879 times services plus 0.288838 times government. It's a PC now. Right there. So in a similar fashion, you can write all the 5 PC5, PC5. And you can have you have a PC1 here, PC2 here, PC3, PC4, PC5, and you have a response. Then you regress. Response will be regress. Let's call this one Y in this case. So Y you can regress now. See, Y equals, see, you can write B naught plus, I'm going to write the model law, that estimated model law, the estimated value. This one PC1 plus B2, PC2 plus B3, PC3 plus B4, PC4 plus B5 times PC5 plus, if you want, you can put error. Without error, you put the head and write it down to show that the estimated value. Let's call it PC, principal component. Principal component. We're going to take into account the only principal component regression. Regression. Principal component regression. See, in this case, that they were just to say that, just to use that one. See, there's a fact analysis one, so you can use that one too. So sometimes you can get the standardized scores, see, GSP score. So here 13, if you want a 13, we can get the 13, see, like that. How many things we can discuss on that one? See, one mixer 5 eigenvector. So you can narrow down eigenvectors and looking into this one. That's the second data set. Okay. I think that drug data set has been given for the second homework, but for the first one, see. So this one, see. We saw this one, see, we got that data, principal component analysis for this one and the correlation. And we were asking them to give the covariance as well, see, correlation under that one, see, go to data. We ran this one. In this data set, another kind of a data set that we're going to list over here. See, another way to that represent the data. So you call this one the fitness data. See, that's the name that we're going to call it from. You put the inputs, age, weight, oxygen, runtime, rest pulse and run pulse and maximum pulse at, okay, data lines. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Sorry, this one. 1, 2, 3, 4, 5, 6, 7. Let me see one more time. 1, 2, 3, 4, 5, 6, 7. Sorry, 7. Yeah. And they keep going. See, let's. So you have the age, weight, oxygen, runtime, rest pulse, run pulse, and the max pulse. So this 1, 2, 3, 4, 5, 6, and 7. We take 1, 2, 3, 4, 5, 6, 7. Yeah. And there are how many data points? Okay, then let's run this one. Then let's see. Okay, then then so here. Okay, it's a principal component regression onto 4 factors. Okay, PCR means the principal component regression, number of factors, see, data. Okay. So then let's see that this one. See. So the PLS stand for what? Here I'm gonna write here for you to get an idea for that. PLS stand for PLS partial least, okay, squares. It's another procedure, okay. Partially, they're gonna look into that one, okay. Sorry, partial least squared, PLS data fitness method, PCR equals to principal component regression. The way of doing that from partial least squares, data fitness method, this one say oxygen. Now we were trying to that regress, okay? We were trying to regress by using that principal component analysis and then regress this one, okay? So age, weight, runtime, run pulse, rest pulse, max pulse, okay? PCR onto 4 fact, where this one. This has been, see, this has been Y variable, see, oxygen. Oxygen mean Y variable, let's see what's gonna happen. It's a principal component regression. Let's see. Parameter estimates, see, all the estimates here. Oxygen parameter estimates entered at the scale data. Okay, that's the procedure they were using over here. So number of extracted factors. See, look at the extracted factors. Only 4 factors. They have extracted only 4 factors. The best one. It has been extracted inside. The same thing that we did over here. When we were running this one, we extracted 5. Here, the 4 being extracted, and those 4 will be regress with this one. Okay. This 4 will be regress with this one. See? So this is parameter estimate. See? 1, 2, see, by this one, see, parameter estimate for the centered position. That's another way of looking at this one. So see, all these, and then we can check that which one's going to be important of explaining this one. Because if you want that, let's say that, look at here. Okay, I'm going to take this one out before that one. I'm going to get this one and run this one, print com, copy. Okay, I'm gonna run something here for you to see here. Okay, I'm gonna get this one, age, weight, pause, max pause. Okay. That means that only principal component, 4 principal components are taken into account. Age, weight, age, weight, runtime, runtime, response, max pause, agriculture, mining, construction, energy, trade, services, government. Okay. Let's say that we're going to cover this one and see, and see whether how many we can. Okay. So print count. Oh, what happened? Oh, sorry. Fitness. Okay. Okay. Let's see here. See, 1, 2, 3, 4, 5, 6. Max pulse. Print 1, 4, 6. It means reduced to 6. See? 1, 2, 3, 4, 5, 6. See? This one. Okay. Let's put this one to oxygen too. Okay. We'll try something here. Oxygen. Let's see what's going to happen. Oxygen, we're not supposed to put oxygen, but see, if that's the case, it's going to reduce to only 2 or maximum 3. 2 of them, according to the scree plot. Scree plot is the one that is called eigenvalues versus the principal component. We're going to do this one more detail. Okay, keep talking about this one next 2 days as well. But for this one, if you take this out and see that how they're going to write the new variables with the linear combination, with the aid of this linear combination. So we saw that they're trying to come up with how many. Let's say the scree plot. Scree plot say how many? 1, 2, 3, 4. See? Oh no, sorry. Almost like a 2, no? See? Almost like a 2. See? Out of this 1, 2, 3, 4, 5, 6, 6 variables, only 2 principal components are taken into account. That means this guy and this guy. So you have only 2 variables according to this, if you run this one separately. But here, see, I'm gonna, since I keep this one, I'm gonna get number of factors. I'm gonna get rid of this one and see how they're gonna do by itself. Okay, let's see. Principal component. Oh, syntax error. Oh, oh, they need, so they need the number of factors. Let's say with the 2. See, this is all the variables because they have to show all the variables they are estimates because those are variables. See, 1, 2, 3, 4, 5, 6 variables are already over there. R squared adjusted. See, model effect. See, number of extracted factors. See, only 2. Only 2. If you put this one, extracted factors 2. See, based on that one, you see dependent variable. See, the percent variation accounted by the principal component. Let's say 69%. See, dependent variable and see 69%. Let's keep this one to 4 and see, okay, as earlier. And then separately we can see that how much variation been explained by the 3 explain. You keep almost like a 78%. So let's see that on this one, if you go ahead and keep this one to principal component to 4, okay, and see whether they're going to contribute the same variations before we do the regression. Almost here, according to this one, almost if you keep the 98%, see, you see this guy, 2 enough to see, 2 enough for you to, sorry, here, see, actually third one, if you want, you can get the third one, 2 all the way up to almost like, below that one. No, here these 2, see, component 1 and 2. So that means related to this one, that will explain this much of variation. This one is like a 65%. See, so, but here that so much not been explained, but according to that rule, we have to keep that one. So if you consistent with that one, it's almost like close to that one. You can just even add another one. Okay, if you want, you can do that one. If that much not been thoroughly explained, see. So then see variation, see, then if you keep 3, 80%. Earlier you saw that when you keep that 4, they were keeping 4 and then see, if you run the regression, they come up with the all the variables and then keep the up to 4, see, regression. For the regression when they run, only thing that when they run the regression, you need the estimates only. You need the estimate for each and every variable. They are here. They are here. See, they are here because that it has been done like a regression, but it's a principle. It's going to be based on the not this one. It's going to be based on the principal component. They were using at least that 4 principal components, extracted 4. Because if you put the 4, then it's going to be 4. Number of factors we have to give that. How many factors you really need? See? At least 4 you need in order to explain that one. So that rather than running this one, you can straight go to this one and run and then get the answer too. And from this one, you can talk about only the components only. Forget about the regression. See, regression part, I was just explaining, but for time being, forget about the regression part. But principal component you can extract from this one. If you feel like that 2 not gonna explain that much of variation, you saw 68% of variation being explained. When you add another one, it seems like it's explaining almost like 80%. But on the other hand, it seems like in order to run and then come up with this one, you really need the 4 components. They extracted 4. Okay, right there. So that we can talk about the rest even that. Okay, I want to talk about these ones too, that keep that discussion that I want to continue. Okay, that on Wednesday, because we have plenty of time, we can just go through all these. That basically that principal component part is the one that I really wanted to explain. That I later on, if later on gonna ask for the regression part, I can explain that one too. Okay, later on, including all these using several different setups. And on the other hand, that for the homework too, that we were using, I think this drug data, drug data has been given, and then they've been formatted, and they have RxPM, GSRI, copy, then everything has been explained over here. The homework number 2, I'm going to come back to see. So here they say the data be more efficiently expressed using PC. How big are the first, second, and third component? You can made for using the interest in data and insight. Use the literature and SAS for point on the interpretation. So if you want, you can use the same data set or that one. I'm gonna little bit go through this one to next time. But if you get back to this one, this homework uses the data set, drug cost, text. The goal is to develop accurate regression model that predict the cost, the variable in the data set, cost, average cost, plan for one prescription per day for 1 day, RxPN, number of prescription per member per year, GS, generic substitution, effectiveness index. This is 0, 100. These are no solution to $100 generic substitute. OP, age, percent female, member month. Perform multiple regression and evaluate overall fit on the raw data. Once you get the data, let's say that we have this data, and I'm going to call that on drugs. Okay. 29 rows and column 9 columns. They have the 9 variables, including 9 columns, and then 29 observations. And we can fit in this into with this kind of multiple regression model as usual. This as of now, that how to roughly, even at least roughly look at that this residual versus quantile kind of very well fitting into this one. You can remember these residuals versus quantile. This is a theoretical quantile. That means this is going to be compared and contrasted with a standard normal distribution -3 to +3. See, they're going to fall into this one very well. And then y value to predicted value. See, cost to predicted value. Look at this one. See, histogram for the residuals, and then this one residual versus a predicted value. Then our students, see, it's not gonna go to a con. They were nicely spread out. That means that linearity and homogeneity can be easily set check on this one. Okay, we can remember. And these are the estimates, their standard error, t value, p value, overall fitting, number of observation, adjusted R, all kind of stuff. You look at the mean square error, only little bit of mean error in left row. So then scatter plot, we can we just draw this one and see what it looks like. Scatter matrix. That. And their selection procedure. That's it. Same, let's see. Put this one and this one. That's all they've asked him about. It's not a big deal. And I would like to that after that I go through the principal component a little bit more. Plus that I would really love to get into the discriminant analysis as well. Then so, the next time, because it's gonna be discriminant and these two. So no, not chapter 11. Series data, if you have, we can go through that one, but I don't think that doesn't permit, and then they haven't given anything on that one. So see, this one look at very interesting. See, dependent variable and introduction to discriminant analysis and logistic. If you get a rough idea here, see each case. See, as I said earlier, see that this same look at the assumptions. Assume we have two predictors x and x2. The regression assumptions say that for each pair of values of x and there's a distribution for y value. See, the distributions mean is this one standard. Okay, that's the same thing. Here, two problems we have. When the regression is estimated, we could get estimated probability bigger than 1 or negative. The other one is normality assumption is violated and sigma is not constant. See, if the normality assumption is violated and sigma, that means that your error or y is not normally distributed, or your sigma from that y variable, let's say that y variable has a certain distribution, we can remember error distribution and y distribution the same. Then you have to remedy this one. Several methods to remedy these two. But when your regression estimated bigger than, sorry, we could get estimated probability, see, bigger than 1 or negative for a certain reason. Worst one, this normality assumption or that homogeneity, homoscedasticity has been violated. How do you remedy? See, discriminant, logistic, and classification. As I said earlier, that principal component come under the unsupervised learning, and the discriminant classification come under the classification come under the for the regression classification and logistic regression, linear regression, discriminant analysis, all this supervised learning. See, techniques that try to see here, essentially using linear regression, but interpreting the output in different output means like a different way. Logistic, a special type of regression designed to fix the violation. Techniques that try to find the rules for group membership. See, classify. Okay, look at here, they say. It's a technique for analyzing data when the criterion or dependent variable is categorical and the predictor independent variables are interval in nature. See, techniques, discriminant you are using when the criterion dependent variable is categorical. It's important. Categorical, dependent. I'm talking about y variable. We never did anything with the y variable categorical up to this point until that we were exposed to discriminant analysis. And the predictor variable means x variable or independent variables are interval in nature. Okay. It is a technique to discriminate between two or more mutually exclusive and exhaustive groups on the basis of some explanatory variable. We're going to talk about the detail. When the site criteria has two categories, adapters and non-adapters. Let's say this one. See, look at how they've been done. Analysis, similarities, number of dependent variables, You have one variable, regression one variable, discriminant, you have one variable. Number of independent variables, ANOVA multiple, that's okay. Difference, sorry. Nature of the dependent. Metric means numeric. Metric means numeric. Quantitative, metric. Regression, metric, quantitative, numeric, categorical. ANOVA, independent variable or x variable, this one categorical, this metric, discriminant. You can see that how they differ from each other. So this one metric is categorical and metric. And the other one coming under this one is called the logistic regression as well. Y variable is categorical, x variables are quantitative. Metric to metric, you always regression, you know that one. Analysis of variance is a group regression in which that x variables are categorical, these are this one, like a rough idea. Assumption, see, group size of the dependent should not be grossly different. Say 80-20, it should be at least 5 times the number of independent variables. See? Each of the independent variables normally homogeneous, homoscedastic outliers, like that rough idea. Okay. Non-multicollinear, there should be multicollinearity, means there should not be any type of that regression, correlation between your own regressive variable. Mutually exclusive means like they are independent of each other. Okay. The group means a set of individuals for two groups versus this one. We come to this one, but I can show you the some kind of example. See, they do like that. So they divide into two groups. They divide into two groups by deciding a certain cut point. Cut points. See? And they say that this whatever that one we cut based on the cut point, you're gonna assign to that group. Zero group or one group. Say example, look at this employee performance categorized as a satisfactory and unsatisfactory. They will be, see, these are Y variable. Y variable for the first time you have a mean categorical. But X1 means the test one and the test two. How many in N1 and how many in N node? See? N1 means what? How many in category one? See? N1. Averages. The averages N1 and N2 means the group one and group two. Two groups. You have two groups. See? One group, first group, satisfactory group, you have 23, unsatisfactory you have 20. The person at direct has to test that she would like to use to help determine which future employee will perform in a satisfactory manner and which will not before they assign to a position. There are data over here, groups over here, and then they run that one by doing certain way that we can figure out, see how they categorize that one too. So later on they come to this classification. See? And then they get this C value. I'm going to go through this everything. Then later on they classify. This classification, if they don't, see, if then their assumptions are not satisfied, that's how they jump into the log. See, it's a special type of regression for the modeling categorical dependent. That's the same thing we do. Apply to predicted data that is not normal. Predictor variable, not normal or content qualitative predictors. So that's a logistic is another type. Okay, these two I like to go through on Wednesday while going through this that and show you how to get all these at the end of the day and get converted into this regression and come up with this all the answers. And you don't have to worry about that that anything because that at the end of the day, see that fact analysis too, I added that one too, little bit we can go through that one and then see. Okay. See. So this one, like this is fact analysis, look at this one. Like an example of fact analysis given in the following scheme. Imagine many students in a school, they will all get the grade for many subject matters. We could imagine that these different grades are pretty partly correlated. A more intellectually gifted student would have higher grades overall. This would be an example of a latent variable because there are hidden variable going to affect to that one. That's over the factor analysis. See, unmeasured variable called the latent variable, common factor. That means they have an example language ability. The other one is example technical ability, common factor 2. Unmeasured variable, latent variables, two variables going to affect that getting grades. Then when they get the grades, see English exam, this is measured variable, this is a hidden variable, measured variable, German exam grade, math exam, those are technical, see, of the sciences, technical subjects. And again, see, specific factor is English specifies skills, German specific skills, or math, or physics. See? They were really good in physics, they were really good in math, but they're not good in German or English. So some people are really good in English, not good in German, like that. But these are, see, those are the factors. See, those are the hidden variable. That means they are really good in English. Then they can do better on this one than do better than do on these two. At the same time, they were really good on English as well as physics. Like that. Those are all the combinations. But those one, when it comes to that grades, those are hidden factor because they have their own skills with them. And that skills will be displayed when they take the exam. See? But they were not measured. These are the measured ones. Your test grade will be measured, not the skills. Skills are hidden one. So those hidden one will be unmasked at the end of the day through the fact analysis. Okay, like that. So these are heavily utilized in that. I think socio-economic, sociology, psychology, and then socio-economic research and all kind of stuff. But we can go through this one systematically because there's not that much left over for us to cover within next 2 days while I'm going through that principal component, discriminant, logistic, and then this fact analysis. Pretty much fact and principal component go together, discriminant and logistic go together, and then we can run some data and then the results and have a look at it and then discuss about that. So what I'm gonna do that I'm planning to stop over here. Do you guys have any questions? Anything? Any question? Anything? If you don't have, what I'm gonna do, I'm gonna wind up over here, and you guys have a good night. And then hold on, give me a second. Yeah, sorry. Thank you. Not currently. Okay. Thank you very much. And then see you on Wednesday. I'm gonna continue this discussion. This is the last week. Okay. So what I'm gonna do that you can finish your all the homework. I'm gonna give one more extra week. Okay, next whole week too. Okay, for you to finish up everything and then turn in everything, and then I can put the grades, finalize the grade, not the coming Tuesday. Coming Tuesday means not tomorrow. I'm not talking about tomorrow. The next, the not the next one, the following one, following Tuesday. So you have a extra whole next week. After that, this 4th week finish, that you have 1 week being given for you to finish all final exam, all the test and everything, and turn in everything. Okay. So you have plenty of time, but don't wait for the last minute, and then because sometimes procrastination is the worst enemy of humans. So just try to get things done and try to turn in everything. Based on that one, I can grade it and then give it back to you. Okay. Since you guys don't have any question, what I'm gonna do, I'm gonna go ahead and stop over here, and you guys have a good night, and stay safe, be well, and see you on Wednesday. Take care. Bye bye. Thank you. Thank you very much. Okay, thank you very much. You have a great night and good night. Take care. Thank you very much. Yeah.